In this clip, we're going to connect the null space that we talked about in the previous clip with a definition that you've seen in your previous courses, which is called injectivity, or for a function to be one-to-one. So in general, if you have a function from a set x to a set y, then this is an injective function, sometimes called one-to-one. If and only if, whenever I take two different points from the domain, it implies that their images under the map are different. So f of x cannot equal f of y. So in other words, two different points cannot get mapped to the same point. Now the only thing is this is a bit awkward to use with proofs because of all the negatives. So we typically take the contrapositive of this statement and we say if f of x equals f of y, then it implies x equals y. And so that's the statement that we will use for the definition of injective. And so it turns out that linear maps are so simple and so rigid that if they are injective if and only if they are injective at the origin. So in other words, a linear map from V to W is injective if the only thing sent to 0 is 0 itself. And so in other words, that means that the null space is trivial, the trivial vector space. Okay. So again, the way I expressed that a moment ago is T is an injective linear map if and only if it is injective at 0. So one-to-one at 0. So let's see. So for the proof of this is an if and only if. So let's do the forward direction first. And suppose T is injective. Now, the thing that we're supposed to prove in this case is a set equality, and that's typically done by doing both containments. So now we already know one direction. 0 is a subspace of any vector space, so in particular it is a the 0 element is contained in the null space, which is similar to saying the 0 space is a subspace of the null space. So we just need to show the other direction. So in other words, we have to show that if anything is sent to 0, that something has to be 0 itself. All right. So suppose we take something that gets sent to 0. Let V be an element of the null space of T. Well, then let's see. So then T applied to V is, since it's 0, it's the same thing as T applied to 0 because we know T always sends 0 to 0. And now if we apply injectivity, injectivity says more or less that you can cancel the T's from that previous equation. Formally, you can sort of think of it like that. Okay. And so then that gives us that V is 0. So the only thing in the null space is 0. So we're done. And now we just have to go in the reverse direction. So for this direction, we suppose the null space of T is equal to 0. And we need to show that T is injective. So suppose we have TU equal to TV. All right. Then we can take the difference And tu minus tv, well, on the one hand, if tu is equal to tv, this is equal to 0. And on the other hand, I can use linearity on the difference. And so then that shows that t sends u minus v to 0, which by definition means that u minus v is an element of the null space. But the null space is equal to the 0 space, so whence? Oh, I got overexcited. There we go. Whence? And we get u equal to v. So here we use the hypothesis. And that's it. Oh, and maybe while we're here, just before I leave, I'll mention, I forgot to mention this in the last clip, but sometimes the word kernel is used. And this is just a synonym for the null space. I've actually seen null space used more for linear maps specifically defined by matrix multiplication, and kernel of T is like the more general thing, but whatever.